Welcome to this workshop, Practical Machine Learning. This is the third day, and we continue. Let me take several minutes to have a short recap what we talked yesterday. Yesterday, we covered two main supervised learning tactics, is regression and classification. We addressed that the supervised learning depends on the labeled data. If you want to predict something, you have to know, or you have to make sure that the prediction is some kind of correct, then that you can have a reference. And actually, this might be not always true in your data, because sometimes you collect a lot of data, some have the label, but some doesn't. And if you want to label this data, it might be costly, time consuming, or even not possible. That is why we are going to have unsupervised learning. There's no necessary for you to have the labels. In unsupervised learning, we only have input features. We want to make predictions to group this data into different clusters or separate them clearly into different groups. The goal is to explore the data, to find the structures, the hidden structures, and learn some useful insight from its own. So it is our role to decide if this algorithm works well, or if this algorithm doesn't work well, then we have to use another one. So we should judge the efficiencies of these algorithms. I would like to address that unsupervised learning is not competing with supervised learning. In fact, they combine together. Unsupervised learning is the foundation of supervised learning. It can be used for pre-training models. I mean, we get some extract. We first group this data into several small groups, or we reduce the dimensionality of this high dimensional data to low dimensional space. Then we can use supervised learning to classify this data or to predict some numerical values from there. So in this and next episode, for today, we will use clustering and dimensionality reduction technique on the penguin dataset to find the hidden patterns without using labels. We will see how it works. This is the supervised learning, representative learning algorithm like PCA, like Disney and UMAP. This is about techniques for the dimensionality reduction. So we will cover this in the next episode. In this episode, I will talk about the clustering. What is clustering? So clustering means that we group similar data point together without using labels. We, depending on some criteria, we put this data together as one group and put the other some kind of data in another group. For example, if we want to cluster the penguins by their features like flip length, body mass, the groups might be naturally match their species. If we have the labels, it is better for us to make a comparison if the grouping is good or not so good. Here we have a figure to show what does this mean. If we say this, we want to group this data in two clusters. This is quite natural. This is one cluster. This is another cluster. And how to evaluate the efficiency of this algorithm, we have a silhouette score, and we can mention this score later when we evaluate the performance of the k-means algorithm. And if we know that there are three groups in this data set, we really want to group this data into three clusters. Okay, from the algorithm, from the k-means algorithm, this is one, reasonable. This is another one. This is the third one. If we say we know there are four groups right here, we want to clusterize this data set into four clusters. From the algorithm, it means this is one, this is number two, number three, and number four. If we know that there are three spaces or two spaces right here, then it's quite natural for us to choose this one. If we don't know, we should judge which one is quite reasonable. And from here, I like this one. This is quite reasonable because I can see a clear boundary between these two clusters or two groups. In the first algorithm, we will cover this k-means algorithm. We want to see how can we characterize the penguins data site. And so in this episode, we will try to use several clustering algorithms on the Penguins dataset and compare their efficiencies. Let's switch to the Jupyter Notebook. Routine procedure, we need to load the dataset from Seaborns, and we want to get the pair plot as species. We did it before. Here we create another one for this clustering task, Penguins clustering. That's a template for the use. And we drop the rows with missing values, and to remove the duplicate and count how many samples in this data frame. We have 333. For this clustering task, there's no output, so we select these 4 features to classify this dataset. And we also use standard scalar to scale these numerical features. First one, we talk about k-means. What is k-means? K-means is a centered-based partitioning method. That is the center-based partitioning method. So it groups data into clusters. We should define how many clusters we want this group to be. We should predefine this parameter, where each cluster is represented by its centroid, this cross mark right here. This cross mark is you can say this is average position of all the points within this group. If you're quite familiar with molecules, you can say this is the center of mass of this molecule. Here we take this image as an example to describe. This is the data. We have lots of data points. Ignore the colors right here. In the first round, we should choose how many clusters we're going to divide this group data into. Let's say 3 clusters. We want this data set to divide it into 3 clusters. Okay, predefine k equals to 3. And so in the first iteration, we randomly generate 3 centroid point like this cross mark right here. This is for the green, blue, and orange thing. And then we assign the data point in this to the closed centroid. What to do? For each data point in this data set, we calculate its distance to these 3 centroid and pick up the closed one. For example, I have this green point. I calculate distance to this centroid, this one, and also this one. Okay, I know this. The closed one is the green cross mark. Then I choose this one it belongs to this cluster. For all these data points in this data set, we generally follow this step, and we can first clusterize into 3 groups: green point, blue point, and orange point. This is the first step, and then we recalculate the central position based on these data points in the in this cluster. For example, after calculation of all these green points, the center position is at this star here, and for this blue point, the center position is at here. This is reasonable, right? And for this orange point, the center position is at here. Then we take a step to update the position of this centroid. That is from here to here, from here to here, and from here to here. This is the first round. And come to this second round. Again, we repeat the same thing. For each point in the dataset, we recalculate which cluster it belongs to. You can see that this time, this green point is right here. It belongs to this cluster. And for this blue point right here, for this orange point right here. And then we update the positions of this centroid. And iteratively until the centroid stop moving. And this whole process is called expectation and maximization. It's listed right here. It means that we follow these steps. We clusterize all these data points in this data set to 3 clusters. 3 is a predefined parameter here. Let's come to the code. We use the k-means class from the scikit-learn. We predefine k equals to 3. We know that we want to group this dataset into 3 clusters or 3 species. From this algorithm, we can construct this instance right here. In clusters equals to k. We want 3 clusters, random state, and initiate means 10. This in 10 steps we cannot change anything. Then we stop this algorithm. Then we feed this algorithm to the training set. We see what is available in the k labels. You can see there are lots of numbers right here, 0, 1, 2. This is the ID. Each penguin, it belongs to cluster 0, cluster 0, cluster 2, cluster 1. And we concatenate this information to the data frame, and we see what it looks like. For each penguin, the space is right here, aligned. The last column is k-means cluster ID. Means we have got the the ID for each penguin right here. Then we can further evaluate and also to see how to visualize this, how to evaluate the model's performance. Here we have 2 matrices. One is silhouette score, the other is the adjusted random index or ARI score. What's the difference? The difference is that for ARI, it is applicable to the dataset with labels. For example, the penguin dataset, we know the labels. That is, we can use this ARI score to measure if this model is good or not so good. It means how well the algorithm recovers the label. I mean, which if this is similar to the classification task. It means we know the label, we have the prediction, and then we make a direct comparison. So a high score means that the result is consistent with the label. Therefore, if we say a score of 1.0, this is the perfect situation. It means everything is matched. 0, it means random clustering, and it's not so good. If we have negative values, well, this is not good. This means even worse, so random clustering. Let me see how if we can compare the ARI scores from different algorithms later. Then silhouette score is another method for the evaluation. It is applicable to the dataset without labels. So if we in the dataset we don't have the labels, then we can use this one to make the evaluation. It means that how well each point fit is assigned the cluster compared to the others. I mean, if one point is assigned to this cluster, and it measures why it is assigned to this one but not to the others. Comparison like this. It ranges from -1 to +1. +1 means that the sample in the dataset are well matched to their own cluster. I mean, well separated. This is the perfect situation for the clustering. 0 means that the point at the border part between clusters, it might be belongs to this one, might be belongs to that one, depend on the situation. -1 means the points may be placed in the wrong cluster. So the larger the score, the better for this model. Okay, we got 2 values right here, 0.446 and 0.8. But from these numbers, it's hard for us to argue why and how this model is. It's good or not so good. We want to have some visualization about the distributions of penguins in each cluster and make a comparison with its true labels. So we take a step further to make the plot. Okay, this is the true labels for the penguin species. We have these labels right in the dataset. The left one is the prediction from the k-means clustering. The red cross mark means the central position. This is one cluster, it's quite consistent with the Gentoo right here. And the yellowish is to the second one. It's quite close, similar to this bluish in the center of the chain strip. And this dark brown something, yeah, it's also right here. But we have 333 samples right here. If we compare one by one, what would be, it is also possible, but if you say you have 1,000 samples right here, how can you make the comparison? And you feel from view eyes, you cannot figure out, we can figure out some a little bit difference, but how can we judge the performance of this model? So we can visualize another one about the penguins across this cluster using the crosstab method. It is right here. How can we obtain this? We use this crosstab method from the pandas. Let's see the figure. Yes, this is quite clear. In cluster 0, mainly of Adelaide with a little bit, we have 5 chain strips right here. You can see the numbers. Cluster 0, we have 124 Adelaide and 5 chain strips. And for cluster 1, it is 119 Gentoo. It means the Gentoo penguin is fully available right here. For the third one, it's mainly composed of chain strip with a small amount of Adelaide. For 22 Adelaide, we have 63 chain strip right here. And this is quite clear for us. We know the efficiency. This algorithm is better. I mean, it's good to separate Gentoo from the others. But for Adelaide and the chain strip, then it's kind of not so good. For this one, there are some chain strip right here. For this one, there are some Adelaide in this cluster. This is the case that we know the label. We know that we should group all these data points in this dataset to 3 groups. But if we don't know, say we don't know the labels for these penguins, how can we make the clustering? Or in your project, you have lots of data. You know that you can get some clusters from this data set, but maybe you don't know how many clusters you're going to have. So you can try. This thing, we need to determine the optimal number of clusters. This is quite applicable to the situation you don't know the exact number. 2 common methods we have, Able method and the Deloitte score analysis. So the Able method, it looks at how tightly the data point in each cluster that are grouped around their centroid, quantified using WCSS score. WCSS is the within cluster sum of squares that calculate the distance of the centroid to each point and then sum the square to get the one score. So if what is WCSS? If we consider that at the beginning, all data point in the dataset belongs to one cluster, then we know that the WCSS is quite large, right? Because we first need to calculate the central position and calculate the distance of the central position to each data point and then square it and take the summation. If we have one cluster, then this value is quite large. But if we increase the number of clusters, let's say we have 2 clusters, okay, we can separate this, the WCSS will decrease. And then if I have more clusters, the value for this WCSS will further decrease. The able point is mean that we need to find a point where the rate of decrease shift from sharp decrease and then to slow decrease. That is the point. We can decide that is the point. That point is the number of clusters we need to know. Silhouette score, when it checks how similar each data point is to its own cluster compared to the others. I mean, if this data set it belongs to cluster 1 and y is not belongs to cluster 2, that is why this score ranges from -1 to +1. So a higher score means that the clusters are clear, have a fully separate and well-formed cluster. Here we need to emphasize that the WCSS helps to qualify how compact of this cluster are. Well, the silhouette score evaluate how well separated of these clusters are. Let's get back to the Jupyter notebook. Want to set maximum clusters equals 15, and then we search from 2 to 16. Then we calculate the WCSS and silhouette score. You can see if we plot this at the beginning, the WCSS score is quite large and it decreases sharply and then quite slow, and we find this critical point right here. For silhouette score, it's quite similar, and here the algorithm can give us the number. The suggested number of cluster is 2. Okay, but we know that in this example we have 3 clusters. How come this algorithm give us that the optimal number is 2? But we need to visualize why it's the algorithm generates this number. Let's continue. If we apply this in cluster to 2, we will see how the data points are separated into clusters. We know we have 3. We take these 3 example, and we also want to see if we choose k equals to 4, what it looks like. We train the model, 3 models right here, and then we visualize this result. All right, k equals to 2, equals to 3, and equals to 4. K equals to 3 means that it specified the 3 penguin species. This is the true state in the penguin state site. But for k equals 2, it seems this is also reasonable, because from here we can have quite clear separation region right here. This is one cluster, this is the other cluster. If we don't know the label, I believe this one is the best situation, because from physically I can see a clear separation of these 2 clusters. K equals to 4, know that there are 4 species in this data set. Otherwise, I cannot see why this algorithm generates such a distribution like this. Print out this information, how many samples in each cluster. From this one, I know that k equals 2 is reasonable, but in reality, k equals 3 is the true one you need to get. This is k-means. We will move on to the next one called the hierarchical clustering. So we switch to the lesson material. We have some theoretical description. Yes, hierarchical clustering is another way to group data without labels. So in a bottom-up scheme, each data point began as its own cluster. I mean, each data point is a cluster. Then we take step by step. Algorithm will join these closest clusters together to evaluate, okay, if these 2 data points are quite close, then we consider this is a cluster. Then we join them together. Based on how near they are, we need to have a threshold for this. This keeps going until everything in a big cluster. Such a structure can be visualized in dendrogram. We will see later. It's a tree-like structure. So you might be confused. This is the tree-like algorithm. Generally, we can get tree-like structure as similar to the decision tree. You can say also random forest or random gradient boosting. But this is the only thing. The tree-like structure is similar, but the mechanism is different. Hierarchical clustering merge clusters or split the clusters step by step to form a dendrogram that show the nested grouping thing. A decision tree split the feature space based on threshold and split to separate the class and predict values like that. And another thing is that decision tree is a supervised learning. We know the label, but hierarchical clustering is unsupervised. We don't need the labels. So in addition, DT or decision tree has ensemble concept. We know that we can combine multiple decision trees together to form random forest and also gradient boosting. But for hierarchical clustering, there's no such concept. It's just as it is. This is the description of this hierarchical and with decision tree. Now we come to the code part to see how it works. The computing is somewhat quite easy. We can use SciPy for this hierarchical clustering, or we can use scikit-learn. We can first demonstrate how to use SciPy to visualize the dendrogram. We first compute the linkage matrix. This is the linkage, and then it's extracting the clusters to fit it. F cluster. The first step is to achieve the linkage to compute 4 hierarchical cluster trees, like a tree structure, sorting all emerges from each data point to a final cluster. The second step is achieved using this F cluster, then which cut the dendrogram to a specific threshold to see how can we clusterize each data point into different flattering clusters. Once we get this cluster information, then we can plot the dendrogram to visualize the tree-like structure. This is the example. We can obtain this later. At the bottom, each is the data point in this data set, and the algorithm will see if the data point are quite close. If yes, they will merge together, and then you can see these branches, and this is the node until we come to one cluster like this. Each vertical line right here is one branch. That shows how points are merged. At the bottom here, if this branch is quite short, means that these two data points or these two small clusters are quite close. That's why they merge together. At here, you can see the vertical lines quite long, means they are almost dislike. This is for the pi. Let's see how it looks like if we run this code right here. The iterated score, 0.4. Later we will compare these scores and also the ARI scores. And we run this. This is the dendrogram we can get for this data set. It's maybe not so quite clear because we have 333 data points. At the bottom level, you can see this is quite, the branch is quite short, and the merge of neighboring branches is quite unclear. But try this. If you have a small data set, let's say we have 10, 20 penguin samples here, you can plot, you can get this dendrogram to see how these points are merged to get a form cluster. If we use scikit-learn, how can we use this hierarchical clustering algorithm? Here we use agglomerative clustering. This is the one class to have this hierarchical structuring. And we run this, we get the score, and we can catch this to the data side. This is for the k-means, number of ID of clusters. This is hierarchical clustering from SciPy. This is the agglomerative. We later will compare which one we will get kind of better performance. You see the distributions of each species in each cluster. This is the distribution. When we plot the confusion matrix, we do compare the numbers right here. For the penguins, you see we have 3 clusters. Adelaide, good, 146. For the gentle, it's also good. The only thing comes to the chain strip. We have 68 sampled right here, and the 11 will consider as Adelaide, and the 57 will consider chain strip. But then we can get some errors from this prediction. Hierarchical clustering algorithm in SciPy and in scikit-learn we get the same result. This is reasonable. Let's move on to another one called the dbSCAN. So what is dbSCAN? A long name is density-based spatial clustering of applications with noise. Okay, you know that this is the database. This is dbscan, and this is a clustering method that group points that are close together, and the marked point is sparse areas and noise. Okay, which means that we can have cluster information. We can also get some noise point. So unlike k-means, that's not necessary for us to tell how many clusters we need for dbscan. And the only thing that the algorithm can find the clusters of any shapes, which makes it good for messy or uneven data. But the thing is that we will also get some noisy point. The algorithm consider that okay, these points are far away from the main cluster, they are just the noisy point. Switch back to the Jupyter notebook. We build this model. We use the parameters right here, IPS and mean samples. So what is IPS? IPS is a radius value, means any point within this radius is considered a cluster. Say if we say 0.55 means any data point, their distance is smaller than this value, then we consider they belongs to one cluster. Mean sample 5 means that if one data point has 5 neighbors, then this can be considered the core point. Otherwise, this is another data point. We use these two hyperparameters to construct this model. We fit this model on the training set. dbscan told us that 3 clusters, perfect, this is what we want. But if you throw 0.5, you might get 2 or 4. You see. And also 44 noisy point. This is not what we want. We want that all the data points can be clusterized, even with some errors right there. Definitely, the noisy point is error predictions, but the thing is that 44 is quite a lot, even more than 10%. Silhouette score and the ARI score. But let's see. The ID for these penguins dbscan cluster is right here, and we need to visualize because from these numbers it's hard for us to figure out what this means. If you see the range for this, -1, 0, 1, 2, -1, these are the noise point from this algorithm. And 0 means this is one cluster, 1 is one cluster, 2 is another cluster. And use cross tab to see the clustering thing. Okay, this is not so good. I can see that mainly for each cluster, this is mainly composed of Adelaide, is mainly composed, fully composed of chain strip, the gentle. But for each penguin species, there are some noise point, and the ratio is a little bit high, less more than 10%. I have provided the exercises. If you come to here, I will describe it to you. If you change the EPS values from 0.55 to 0.5, 0.8, keeping the mean sample equal to 5, you can get different results. I mean, it can be 4 clusters, it can be 2 clusters. You will see how you can visualize this result to see why and which one is reasonable. Let's move on. So after we explored the centroid-based method like k-means, hierarchical clustering, and the density-based, this is dbscan, we turn to attention to model-based. Gaussian is one type. What is model-based algorithm? It assumes that the data is made of a mix of probability distributions. I mean, each distribution represents one cluster, and the algorithm tries to figure out both the clusters and the details of this distribution. It can depend on the distribution. There are multiple algorithms. For example, if we assume that the data in this data point in this cluster is Gaussian distributed, then this is the Gaussian distribution. If it is Poisson distributed like this, then this is a Poisson model. Here we use this Gaussian model. Take example, this is a Gaussian mixed mixture model. It's called a GMM. In this algorithm, it assumes that each cluster can be represented by multivariate Gaussian distribution with the mean and variance. Therefore, for each data point in this cluster, GMM will give a probability distribution that it belongs to different clusters. This means that for each data point in the dataset, it has different probabilities belongs to this one. It has another probability to belongs to another one. This is the model-based algorithm. Code part. Theoretical part is quite easy to understand. We want that the distribution of one cluster is Gaussian distributed. Then we want to fit what kind of Gaussian distribution we can get from this model. We use this one Gaussian mixture from this scikit-learn. N component, we know that we have three spaces right here. We want N component to be 3. Covariance type is 4. It means that which control the shape of this cluster. 4 means that each cluster have its own shape. It can be spherical, it can be ellipse. We fit this model and we get the silhouette score and ARI score. We can compare this later. We concatenate the number of ID GMM cluster to the data frame. Then we get the exact numbers for each cluster and the distributions of penguin species in each cluster. Let's move on to have the confusion matrix. Okay, for the gentle, it is good. This species is fully available right here. For Adelaide, 2 missing, and for the chain strip, 3 missing. I can see this is good if we say compared to the previous one. Previous we got 44 right here, but that is not for this 44 sampled from Adelaide, from chain strip, from gentle. Here we only have 5, and from these 2 species. And here we visualize the shape of the cluster. Here we make a comparison of k-means and GMM. We see it. Fitting this k-means model, and we fit this GMM model, and we make this plot. Right. Left is for this k-means. You can figure it out. The central position is the central part, right here, and this one. But for this elliptical cluster, the central part might be right here, but the shape is different. Note that the GMM can capture more points and does not consider them as noisy. They can be labeled right here. This is GMM. We come to the last one about the spectral clustering. Let me get back to the theoretical description. What is spectral clustering? It works differently. Instead of just using distance or density or probability, it uses graph theory. This is definitely a concept in computer science and also in mathematics. Graph theory, the idea is to treat the data type as a graph. I mean, each data point is a node, and the linkage between neighboring nodes as edge to see similarities. The algorithm will first compute the eigenvectors and then transform the data from high dimensional space to low dimensional space. And after that, it's feasible to perform clustering and other tasks. This is the description of the theoretical part, but maybe not so easy to understand. Let's come to the code part. We build the model. I build this model. We want to have 3 clusters right here. Then this is RBF. This is the Gaussian kernel. We mentioned this before. It includes some nonlinearity in this model. Gamma, they control the width of this Gaussian distribution. And also we want to use k-means, both the spectrum and those k-means for this clustering thing. From this, and we build this model and also make the prediction. We have the silhouette score and the ARI index, and we visualize this. again, confusion matrix. Okay, we make a comparison. This is for Clemens, this is for GMM, and this is for spectral clustering. You can figure out. But for here, you can see that we can get a large difference for this spectral clustering. 25 of chain strip were 25 identified as added right here. The reason might be that this is quite a small data set, and the algorithm is good, but the data set is not so powerful that they can get quite a limited training set. So theoretically, this algorithm could be special for to cluster when we have quite a complex patterns or non-convex shapes. That's the hard for K-means. I mean, K-means always get a linear separation, but for the spectral clustering, it will fit the model to vary the shapes. We have the exercises about this two moon data set. If you come back to the part, we have the same data. Two moon, this is from the scikit-learn. If we use K-means, always get this linear separation, but this is not good because we want this is one type of cluster, this is another cluster. But for the spectral clustering, it can be have quite a clear separation for this. Yeah, take this one as an example to see how it works. Finally, we provide the comparison of these models, especially the silhouette score and the ARI score, to see which one is better than the others, and also we provide the short summary about all these algorithms we mentioned right here. K-means, centroid based, hierarchical clustering. We have this SciPy and so scikit-learn, also density based, the DB-scan, and it's model based, the Gaussian based, this is GMM, spectral clustering, this is the graph based, and the K character, the points and the limitations for each algorithm. All right, this is this episode about clustering. Short summary with what is the clustering. It's about grouping data depending on the similarities to different groups, different clusters. Representative algorithms, we have K-means, DB-scan, GMM, and spectral clustering. We always use a silhouette score if we don't have this label, true label for this data point. If we have the label, then we can use ARI score for this evaluation. So I would like to highlight that no single algorithm is the best one. So the right method depends on your data, the size, the type, the shape, and also what you want to get from this training. Let's continue to the next episode. That is the last one about the second domain of unsupervised learning, that's dimensionality reduction. So in the last episode, we talked about the clustering, which is an unsupervised machine learning method that group similar data point based on their features without the labels. If this data point are too close, we can group these two as a cluster. Depending on the algorithms, like centroid-based method, like K-means, like hierarchical clustering, like a density-based method, like a DB-scan, model-based, we performed Gaussian mixed models, like GMM, and also the spectral clustering method. This is graph-based method for this clustering. These are the representative method for this clustering task. A big thing is that the clustering, it can help us to find the hidden patterns of the segments in the data set. If we don't know the label, we can evaluate the performance of each model and using the other criteria. I should say that even we talked a lot about the clustering, so clustering things is also has some limit. Yeah, definitely. We always start from here and to the next one. It's hard to decide the right numbers of clusters, like K-means, like we need to let the algorithm know how many clusters we need. And even for the others, GMM, there's no necessary for us to tell this model how many clusters we need, as this algorithm can tell us, but then we should evaluate the effectiveness of this model. If we set a different k value for this for k-means, we might get different results. I showed that if we set k equals 2, k equals to 2, equals to 3, and equals to 4, we can get a totally different distribution of this data point in clusters. And the results depend on the distance measurement and the feature scaling, which may change the outcome. So in high dimensional data, the clustering will struggle because the distance stops being meaningful, which is called the curse of dimensionality. If you have a loss of data, you need to calculate the distance. This is not feasible. This is not feasible for high dimensional data. In 2D, in 3D, it's quite clear for us. We can calculate the Euclidean distance and also straightforward distance between the data point. But in high dimensional space, you can calculate, but it's difficult to visualization. Its understanding is also take time. That's why we come to another domain. This is about dimensionality reduction. This one is we want to simplify the complexity in this model so that we can use this data for the further supervised or unsupervised learning, or even semi-supervised learning. The common method for this dimensionality reduction include the PCA. This is principal component analysis. We want to transform the features to component. I mean, we can transfer the 4 features to 2 components. This kind of reduce the dimension from 4 dimension to 2 dimension. T-SNE, it is the T-distributed stochastic neighboring embedding from the long name, but this is also the clustering to reduce the dimensionality. And but this one, to the most cases, just use a tool for the visualization. I will tell you why later. And the UMAP is the uniform manifold approximation and projection, the long name for this. But this is also another one. This is quite effective for this dimensional reduction. A good point is that once we reduce the dimensionality, we can also apply the other algorithms like k-means. We can combine UMAP, UMAP, and the k-means together. After we reduce the dimensionality, and then we can use k-means for the clustering. And even we can use the others, for example, KNN for the regression and also for the classification. In this episode, we apply this dimensionality reduction technique to apply them to the penguins data set. Again, I prefer this penguins data set. Even it's quite small, but we can extract a lot of things. We can apply this data set to perform lots of tasks. Our goal is to project these multiple features into a simple low-dimensional space for better visualization. We come to this Jupyter notebook. As usual, we import these packages and we load the penguins dataset, pairplot, data processing, and we remove these rows with missing values, remove the duplicate, and we extract the species as one column for this. X, this is training set. We use 4 features: build length, build depth, flip length, and body mass. These are 4 numerical features in this data set. And we applied the standard scalar to standardize these numerical features. We first talk about PCA. So what is PCA? It's the linear combination of original variables. We can say that we combine the original variables, original features linearly and create new features. So why do we need PCA? A straightforward point is that we need to reduce the dimensionality. In this penguins dataset, you can see that we have 4 features right here. This is the 4-dimensional space. We can have this, but it's difficult for us to visualize the distribution from from build length, from build depth, flip length, and body mass. We can only, for 2D is quite clear visualization. 3D also possible, but 4D impossible. That's why we need these techniques to reduce the dimensionality. We can say that the PCA is like to compress this data from high dimensional space to low dimensional space. Here again, we use this penguin staticide. We have 4 features. This is the 4-dimensional space. For the PCA, it's quite straightforward. We construct the PCA model, and N component is that we need to specify how many components, the number of components we need to get, we need to compress. For example, 2 is that we need to compress this data from 4 dimension to 2 dimension. We can specify 3 or even 4. 4 means that there's no data compression, just a transformation from one space to another space. When we apply the number of components equals to 2, means that we'll get 2 principal components. Let's run this code. Okay, the explained variance of PC1 is 70%, like this. The second is 20%. What does this mean? This means that in this original dataset, 7% information is retained in the first principal component. 20% information is retained in the second principal component. In total, 90% is retained in these 2 principal components. Means only 10% information is missing from this data compression. We'll see what it looks like. This is PC1, this is PC2. We can see that each penguin has its own contribution to this principal component. But what this value mean, we can describe this later. So the first thing is that we have these 2 principal components. We can just use 2 components, and these 2 components will retain 90% information from the original data set. We can have a plot of this. We reduce this from 4-dimensional to 2-dimensional space. Principal component 1 and 2. If we say we plot based on species, you can see the kind of quite a clear separation of genital from the others. But if we get a plot by island, no, I don't think so. You can see the base joints here, but the loss of scatter right here. On those for the sex is not possible because the male and female are kind of mixed. Even there is a clear boundary right here, but that's not sex-based, it's a species-based separation. This is for the case, simple case with 2 principal components. So a natural thing might arise. How many components do we need? We can say that here we use the 2 components to retain some information from the original data set. But the left 10%, is that important or not so important? We come to another case. That is, we don't want to lose any information. That's why we specify that we need 4 components. 4 components means that all information in the original dataset will be retained, but transformed from 4 features to 4 components. It's a linear combination of these features. The reason is that we want to know how many or why we should retain 2 or 3 components. We apply this. You can see the first principal component will retain 70, the second is 20, the third one is 10%, the last one is 2.7%. Okay, this might be okay, ignore this. If we say the first 2 components, we can retain 90%. The first 3 means 97% information. If we believe that 90% or 97% information from the original data, that is enough for my project, then it's done. If we say 90% is okay, then you can use 2 components. This will save time and computer resources for the training. If we say 90% is not enough. I want 95, 97. Then you can apply 3 components right here. This is the accumulated value for each component. When we come to the first 3 components, we can retain 97.3 information from the original dataset. We concatenate these 4 components to the data frame to see the contribution of each penguin to this principal component. Then we transform the contribution from each penguin to each feature. You can see here is the table. I listed the contribution of each feature to each component. This correlation var comport means the correlations between variable or feature to each component. It ranges from -1 to +1. +1 means +1 means the strong positive contribution, like this one, flipper lens to PC1, the first component. If 0 means there's no correlation of this feature to the component. -1 means to have a strong negative correlation. You can see that the build depths have a negative contribution to the first component right here. For each feature, it can contribute some positive, negative, or neutral contribution to each component. In reality, what we care is about the squared value of these contributions. That is called cosine squared value, which gives the proportion of each variance to a variable that's explained by the component. We can visualize the relative contribution of these features to these 4 components right here. Let's see. Here is the contribution of each feature to each component. Body mass contributes 80%, 82% to the first principal component and less. From here, that maybe the first 2 components are enough to make the first predictions using the other algorithms. If you really want more, you can retain the first 3 components right here. It will retain 97% of the original of the information in the original dataset. But we can go a little bit further and to visualize the correlations of between these variables or between these features and also this component. We have this correlation circle. In this circle, you can see. Okay, we go back a little bit to see the build depth. It contributes 0.4 to the PC1 and 0.5 to PC2. You can see in these 2 plots, this is PC1, this is PC2. The build depth is here. It can visualize, it can mark this point at this 2-dimensional space. And this is for PC1, PC2. Definitely you can have PC3 and the PC4. You can have multiple 2D plots like PC1 with PC2, PC3, and PC4 to see the contributions of each feature to this component. And these correlations can describe the vector direction right here and how they contribute to each component and also the vector length. You can see the length, the radius for this is 1, means quite a strong correlation with this, but here is the row is too short, means quite a small contribution to this component. This is reasonable. We see build depth, it is here. You can scroll a little bit to see build depth 0.067, 003 of manual contribution to the PC3 and also PC4. Right, this is a general a little bit extension for us to have a better visualization of the correlations between features and component. We move on to the next one about the Disney. We mentioned about the PCA. PCA works okay, but actually it's assumed that it's a linear combination of all features, which means that the combination of features, the space is a linear transformation from one space to another. And because of this, what about the limitations? It may miss complex nonlinear patterns because everything is linear right there. And it tries to capture the all variations, but it can ignore some local clusters or hidden groups. That's why we want to include some nonlinearity between the correlation between features and the component. To deal with, we can have more advanced algorithms, let's say Disney and UMAP. These methods are very good at keeping track of local relations and also show the nonlinearity between the features and the components, and also the nonlinear transformation between two spaces. Disney is the tool for reduced dimension, especially for making 2D and 3D visualization if we have a high dimension data. So unlike PCA, it is nonlinear. That's why we should have it will capture the nonlinearity and focus on keeping nearby points in the original data close together to the low dimensional space. I mean, in high dimensional space, if the data point is quite close, and also in the dimensional space, low dimensional space, this data point and also quite close. Code description, you see, we also need to specify number of components right here. To component perplexity 50. This is a parameter to control how many neighbors each point will look at. If we say we will look at 50 neighbors to see if this is one component. If we say what say 100 data points nearby, we may get it a little bit different. This is a control about the complexity and to find the local structures. A high value means capture more global patterns, but a low value, let's say 10, 5, will only focus on the local area. If we say the near 5 point, you can get really the local patterns, if there are some patterns right there. Yes, we run this, and we get 2 PC, and still, because we said this number of component is 2, then we get the PC1 and also PC2. We make the plot to visualization. All right. Seems if we say Disney by the 2D plot by species, this is reasonable. We can have a clear separation of this gentle from the others. But for the island and the sex, it's not applicable. We move on to see what we will get. This is one limitation about the Disney. We say that we have multiple clusters. We want to classify into. We want to apply a clustering algorithm to classify this data into several groups. Let's say this is the 9 clusters right here, and the Disney will classify this into 9 clusters. But also there are some limitations for the Disney, and resulting the bed should be not be used. I just want to demo why we should not use this one for the classification, because if you run this code multiple times, you can see the changes of this data point. That is that you can reduce the dimensionality, but it's not applicable to use the obtained data in the new data space for the predictive task like clustering, like regression, and or even clustering is not possible. This is the main limitation of Disney. So mainly it is used as a tool for this visualization. I mean, we reduce the dimensionality, we will see how it looks like. That's it. If you really want to apply for the following tasks like regression or clustering, I recommend to use UMAP. What is UMAP? UMAP is uniform manifold approximation projection, long name like this. Though this is another method to reduce the dimension. It is kind of like Disney, but with more difference. UMAP keeps these local and some global structures of this data. Usually it's faster and works better on the big data. You can use it for the visualization of 3D and 2D. I prefer 2D because you can get a better understanding where the data distribution right there at the processing step before clustering and also classification. So later we have the exercises. After this UMAP, we reduce the dimensionality from 4D to 2D. Then we can apply a clustering algorithm to see how can we group this data into different clusters. The theoretical of UMAP is based on two concepts. This is the manifold learning and the graph theory. Or this part might be not easy to understand. So manifolding that even if the data has many dimensions, UMAP assumes that the real shape of the data is similar in the low dimensional space. So they try to capture the shape and also the hidden patterns in the low dimensional space. The graph theory is another thing. It's assumed that UMAP treats a data like a graph. Everything, each data point is a node, and the link between each pair is a bridge, where each point is node and lines connect to the data point. This can be a graph thing. Then UMAP use this math to flatten this graph from 4D to 3D and to 2D, keeping all structures. The main key point is that UMAP want to simplify this high dimensional data and reduce the data, compress data from high dimensional space to low dimensional space. So how does this work? The UMAP will build a graph of data high dimensional space and the map to this low dimensional space. We can visualize the data in 2D, in 3D. Comparison of UMAP and the Disney and the PCA and the UMAP strikes a good balance of complexity and also computer efficiency. It is that's why in kind of machine learning or deep learning frames, this UMAP is widely used for the data analysis. We come to the code part. The instruction, we specify n component equals to 2. I want to see the number of neighbors, 10 neighbors to see this, and feed the model on the training side, and then we concatenate the obtained PCs to the data frame. And here we will feed this model and then make the predictions. Then you can see how it looks like for PC1 and for PC2. Here is comparison. If we prepare the 2D plot based on species, based on island, and based on sex, we still get the similar results as before. Oh, yes. This is for species based, this is island based, and this is sex based. Again, I like this, gentle is well separated, but for the island sex based, this is intrinsic to this penguin's data set. Is not related to the algorithm. Okay, I mentioned this before that we can use this obtained component to have further tasks like clustering. So here we use k-means combined with UMAP we first reduce the dimensionality from 4D to 2D and then apply the k-means to classify, to group this data into different clusters. We choose 3 clusters, 5 clusters, and 7 clusters. We'll see what we can get. Yes, this is after the dimensional reduction. We get this data in PC1 and PC2. And for the clustering, we use the k-means. We need to get 3 clusters, and this is 1 cluster. This is not the cluster, this is the cluster 1. The cross mark the centroid position of these clusters. If we want 4 or we want 5, this is 1, 2, 3, 4, 5. If we want 7, we can see that the combination of UMAP and the k-means, we have a better understanding. So in practice, if you want to group your data into different clusters, you can do it at first, but if you have a high dimensional data, maybe at first you should reduce the dimensionality from high dimensional space to a little bit lower dimensional space, then perform the clustering. All right, this is the end of this. I gave this to you, perform this one, and also the Jupyter is there, and have a short summary about this section. We use the PCA, Kisney, and the UMAP to perform the dimensional reduction task. PCA is good, and we perform the 2 cases, and PCA with 2 means that we want to reduce the dimensionality from 4 to 2. Kisney, it is always a tool for this visualization. It's not applicable to, we can reduce the dimensionality, but it's not applicable for the following task like clustering, like classification. But UMAP can do this. So you can use UMAP to first reduce the dimensional reduction and then apply the clustering task to classify this group into different clusters. It's time for the exercises. Let's play with the code for 20 minutes until 11:50. Then we have a short wrap up.